Okay, can you see my screen?
Yes, sir.
Yes, sir.
Okay. So we were discussing phasor groups of three-phase transformers, and so far we have completed YY0, DD0, YY6, DD6, YD1, YD11. Okay. So today we will start with these two, DY1 and DY11. So DY1 means the high voltage side or the primary side will be connected in delta and the secondary side will be in star, and this secondary line EMFs will lag the primary line EMFs by an angle of 30 degree. Okay, so this is minus 30 degree phase displacement. So let us consider this as our primary side terminals A2, B2, C2. The phases are yet to be identified. Now before that, let us draw the reference line, and with this reference line 30 degree phase lag will be like this, and this point is B2, this point is C2, so we can draw B2 here, C2 here, and A2 like this. Okay, so this is the secondary side or LV side Y connection, making an angle of 30 degree with the line EMFs of the primary side. Okay, now we have to identify the phases. Now see, this line is C phase, so this has to be our C phase. Okay, now to make this one C phase, this terminal has to be C1. Okay, then this one parallel to this side, so this has to be our B phase, and to make it this terminal has to be B1. Okay, and this one is our A phase, which is parallel to this line, and to make it A phase we have to assign this terminal as A1. Okay, now the phases are identified. Okay, so this is C phase, and the phases are also directed in clockwise direction. Okay, so A1 to A2, B1 to B2, C1 to C2. Here also C1 to C2, A1 to A2, B1 to B2. Is it clear?
Yes, sir.
Now draw the connection diagram. Very simple. So A2 B1 connected, B2 C1 connected, C2 A1, and the output input terminals are A2 B2 C2, and in case of secondary side or low voltage side, all the wall terminals are short circuited and the outputs are taken from A2 B2 C2. Any question? No. So let us go to the next connection. This is the neutral terminal in case of low voltage side, which is star connected. So going to next connection, that is DY11. Okay, here the low voltage side EMFs, line EMFs will lead the high voltage side line EMFs by an angle of 30 degree. So this is positive 30 degree phasor group. Okay, so again let us draw the equilateral triangle having vertices A2 B2 C2, and this is the equivalent star. Okay, now make an angle of 30 degree with the reference line, and These are C2, B2 terminals and then A2 terminal. Now identify the phases of primary side. So this one is B phase, so this will be our B phase. This one is A phase, so this will be A phase. This is C phase, so this one will be C phase. So accordingly we have to assign the terminals. So B1, then A1, A phase, C1, C phase. Okay. In earlier connection, this was C phase, this was B phase, and this was A phase. Now see, the position of phases has changed, but the vertices A2, B2, C2 that remains fixed. Okay. So the angle between V A2 B2 and V small a2 B2, that means between this side and this side is 30 degree. Clear?
Yes, sir.
Yes, sir.
Now draw the connection diagrams. So the connection of secondary side remains same, only the primary side connection will change. Here A1, B2 are short circuited, B1, C2 and C1, A2, and the input terminals remains fixed. In case of secondary side, all one terminals are shorted, outputs are taken from two terminals. Okay. Now next we have all the Z connections. Okay, DZ0, DZ6, YZ1, YZ11. So first let us consider DZ0 and DZ6. So DZ0. So this is our primary side phasor diagram. Phases are yet to be identified. So let us assume this phase as A, this as B, and this is C. Okay. Now before connecting the secondary side in zigzag, if we excite the primary side, the different phases of low voltage side or secondary side will be oriented like this. Correct? If this is B phase, so these two are B phase, this one parallel to this phase, and if this is A phase, so these two are A phase windings of secondary side, and these two are C phase windings. Okay, so in this type of transformer, all the three legs will carry three windings, one for high voltage side and the two for low voltage side. Okay, so this is the orientation of phases before connecting them, before connecting the windings in zigzag connection. Now with these phases we have to form the Z connection, and the angle between the line EMFs will be 0 degree. Okay, now in order to do that, we can shift these phases parallelly. Okay, or we can reverse the phases by connecting in opposite way. That means if we short all the one terminals here, then the phases will be oriented like this. but if we short all the two terminals, then their direction will change. Okay, so we can change the direction by changing the connection, or we can shift all these phases parallelly. Okay, so how to make this Z connection? Now before that, we have to make the Z connection in such a way that the line EMFs between high voltage side and low voltage side will be 0 degree. Okay, which means suppose this is the equivalent star of primary side, so we have to form an equivalent star with this Z connection, which is same as that of primary side. That means this side will be parallel to this side will be parallel to this side, and this side will be parallel to this side, and this star will be the resultant of this zigzag connection. Like if we draw in this way, so this is one phasor, this is one phasor, their resultant is this. Similarly, we can draw in this way and in this way. So this is this Z connection, and these are the resultants. Okay, so in this way we have to make connections so that the resultant of any two phases will give you the equivalent star connection or star phasor diagram, and those phases will coincide with these phases, equivalent of this delta connection. Is it clear? Okay, let me show you one by one. So this is our resultant delta of zigzag connection. So this terminal is B4, this is C4, this is A4, which will coincide with A2, B2, C2 respectively. Okay, so A4 and A2 will coincide, B2 and B4 will coincide, and C2 and C4 will coincide. So this is the equivalent delta of this zigzag connection we are going to draw. Okay, and this is the equivalent star. Okay, so this side and this side will coincide, this side and this side will coincide, and this side and this side will coincide. Okay, so this is the resultant star, this one is the resultant star of the zigzag connection which we are going to draw. Okay, so how to make this star? Using these phases only. So first of all, take this one. So here to make this B4, we can draw this phasor, or we can shift this phasor from this position to this position, and that is parallel shifting. No problem with that, that is permissible. We can shift this phasor in this position so that this A4 and A4 that remains fixed, so that is also parallel shifting, and C4. Okay, this is also parallel shifting. Okay, up to this it is clear?
Yes, sir.
Okay, now to make this one as a resultant of two phases, we need one phasor here, isn't it? Along this direction, we need one phasor, so that the resultant of this one and this one will become this phasor, NC4, isn't it? Similarly, at this position, we need one phasor to make NA4 as the resultant of this phasor and this phasor. Same way, we need one phasor here. Now tell me which one out of these three, which one will be this one, which one will be this one, and which one will be this one? Tell me first this one.
Sir, C3 to N will be B1, B2.
No, suppose this terminal is C3. Obviously, this is C3 as this is C4. So, what will be this terminal?
Sir, B1.
Yes, B1. Why it is B1? Because we have to shift, we have to reverse the direction of this phasor. Okay, this is actually directed from this point to this point, that is from B1 to B2. But B1 to B2 position will be here. But that will not give us the correct resultant or desired resultant. Okay, so we need to reverse the direction of this phasor. So here it will be B2 to B1. Similarly, here A2 to A1, we have to reverse the direction of this one also. Same way, this one C2 to C1. That means we have to short all the two terminals, and we will get the reverse phasors of these three, and this will make the complete phasor diagram, and we will get the desired resultant as this one, and this one. Is it clear? This is the complete phasor diagram. Any doubt?
Sir, once more, like why we are changing the polarities for these three?
If we don't change, then the position of this phasor will be like this.
Okay, so like the directions will be different, so we cannot find the
Yes.
resultant.
No,
Okay, okay.
we don't get the resultant, our desired resultant, isn't it?
Yes, sir.
So this is not permitted. So this is our phasor diagram. Now based on this, we have to draw the connection diagram. Okay, so connection diagram for primary is very simple. So in secondary side we have 6 coils. In primary side 3 coils, secondary side 6 coils. So primary connection is very simple. A1 B2, B1 C2, C1 A2, and the input terminals are A2 B2 C2. Okay. Now in secondary side, first of all we have to short all the two terminals. Then from one terminal we have to connect the three terminals. So C1 to A3, A1 to B3, and B1 to C3. Okay. So A1 to B3, B1 to C3, and C1 to A3, and this two terminals, this is the neutral point. So we have to bring that neutral point out also if we require. So and the output terminals are all four terminals, A4, B4, C4. Is it clear?
Yes, sir, but wait for a second, sir. Circuit I'm drawing.
Yes, sir. Just wait.
Okay.
Thank you, sir.
Done?
Yes, sir.
Okay. So now DZ6. So the connection of primary side remains same. The phasor diagram remains same. So the connection will also remain same. And before connecting the low voltage side, the orientation of phasors are like this. Now to make Z6, that means opposite to that of the previous one, what we have to do, first of all we have to reverse the outer three phases. Okay, here the direction of phases is of suppose B phase, B1 to B2, that is why it is C2 B2. Okay, now to get the opposite phasor we need C3 B3. this one will be reversed, this one will be reversed, and this one will be reversed. So these two terminals will be B3 C3, okay, and this one will be A3. So that is the mirror image of this phasor diagram. So that the angle will be 180 degree. Okay. Now the equivalent star will be like this. So we have to form this star as the resultant of zigzag connection. Now we have the three output terminals, so we can draw the three phasors. Here this phasor will be B4 B3. At this point it will be B3 B4, this is B3, this one parallel to this side, so this point will be C4, and this one parallel to this side, so this one will be A4. Okay, so in this way we can draw. So first of all, draw B4 B3, A4 A3, and C4 C3. You can see we have reversed the direction of these three phases to get the 180 degree phase shift. Okay, here this phasor is directed from left to right, but this phasor will directed from right to left. Correct?
Yes, sir.
This will produce 180 degree phase shift. Okay. Now this three phasor, where to draw it? One phasor we require here, another here, another here. So
Sir,
this phasor will be, yes.
sir, B1 will be at neutral and B2 will be C4.
Repeat. Yes,
Sir,
yes, yes. All the one terminals will be shorted. So this phasor, first of all, identify this one. Which one is parallel to this one? Obviously this one. So A2 will be here and A1 will be here. Identify this one. This side is parallel to this side. So
C1,
this will
C2.
be C1, C2, and this side is
C1.
B1, B2. So draw A1, A2, B1, B2, C1, C2. Clear?
Yes, sir.
So resultant of these two is this one, resultant of these two is this one, resultant of these two is this one, and see, it is mirror image of this star. Okay, so the phase angle difference between line EMFs is 180 degree. Okay, so this is our phasor diagram. Based on this, we have to draw the connection diagram. So primary side connection diagram remains same. Secondary side, here all the one terminals are shorted, and then from two terminals the four terminals are shorted. So A2 B4, B2 C4, C2 A4, and then from three terminals outputs are there. Outputs are taken from all the three terminals. Clear? Here the angle between suppose V C2 B2. or we can say B2 C2. Now as the direction is in this way, so let us say V C2 B2. Okay, and V C3 B3. They are opposite in direction, so angle is 180 degree. These are the line EMFs. You can consider the other two line EMFs also. They are also 180 degree apart from each other. So that is the neutral point if you require. Any question up to this?
So can I just wait for a minute, so we'll draw it.
You can take a snapshot. Done?
Yes, sir.
Okay. So next we have YZ1 and YZ11. Okay. YZ1 is minus 30 degree phase displacement. YZ11 is minus plus 30 degree displacement. Okay. So let us consider YZ1 first. So Y connection will be like this. So here this one is A phase, this one B phase, this one C phase. So before connection, the low voltage EMFs will be oriented like this. That means parallel to this side, these two, parallel to this side, these two, and parallel to this side, these two. Okay. So we have to make 30 degree phase displacement. That means the secondary or low voltage side EMFs, line EMFs will lag the primary side line EMF by an angle of 30 degree. So this is the reference line. Draw 30 degree phase shift. So that is 30 degree lag B4 C4, and this is A4. Okay. So here this is the position of B3 B4, this is the position of A3 A4, and this is the position of C3 C4. That is obvious from this diagram. Okay, we just have to shift them parallelly. Okay, so equivalent star is this. So if you draw this star here, you will have 30 degree phase displacement with this line and this line, this line and this line, and this line and this line. Okay, there will be 30 degree phase displacement. Okay, and this line will lag this line by an angle of 30 degree. That is the resultant of equivalent Z. Okay. So we need to draw the phasor diagram. So first of all, draw all the outer phasors, that is A3 A4, B3 B4, C3 C4. Now to complete this triangle, we need one line here, one line here, and one line here. So identify these three lines. So which one is this one?
Sir, negative of B1, B2.
Yes, that means
Negative.
B2 B1, B2 B1.
Polarity changed.
Yes, that means we have to reverse the connection, and this one C1 C2, and this one A1, sorry A2 A1.
C2 C1 and A2 A1.
Yes, we need to short all the two terminals. So here A2 A1, B2 B1, C2 C1. Okay, so this will give you the desired resultant, which will lag the high voltage side EMFs by an angle of 30 degree. So we will have 30 degree phase displacement between line EMF high voltage side and line EMFs of low voltage side. So phase angle between V B2 C2 and V B4 C4 is 30 degree. Okay, and this one will lag this one by this angle. So minus 30 degree phase displacement. Okay, so this is our phasor diagram. Based on this, we have to draw the connection diagram. Primary side is very simple. We need to short all the 1 terminals, and secondary side we have to draw as per this phasor diagram. So all the coils are given. All 1 terminals are shorted here. Outputs are taken from all the 2 terminals, and this is the neutral. And in secondary side, all the 2 terminals are shorted, and then 1 terminals are connected with 3 terminals, A1 B3, B1 C3, C1 A3, and then outputs are taken from all the 4 terminals, and this is the neutral. Any question? Anyone having any question?
No, sir.
No, sir.
Okay. So next is YZ1, YZ11. So that is plus 30 degree. So here the low voltage side EMFs will lead the high voltage side EMF by an angle of 30 degree. Okay. So let us draw the planning diagram. So this is our planning diagram. Okay. So now this C4 B4 will lie in this way, and A4 position of A4 will be here. Okay, previously it was here. So based on this planning diagram, we can draw the equivalent star, and on this diagram we can draw the A3 A4 B3 B4 and C3 C4 phases first of all. So A3 A4 will be here, B3 B4 will be here at this position, and this is C3 C4. Now to complete this phasor triangle, each triangle we need the other phasor. So one phasor will be required here, another one here, another one here. So identify these phasors. This one, what is this one?
Which one?
Sorry,
This
2A1.
one. A2 A1. This one,
C2 C1.
C2C1.
yes, and this one B2 B1. So all the 2 terminals are shorted, right? So that is the complete phasor diagram for YZ11 connection. So the connection diagram for primary side remains same. All the 1 terminals are shorted. Inputs are given to all the 2 terminals, and this is the neutral. In secondary side, all the 2 terminals are shorted. Then connection A1 to A3, B1 sorry C1 to sorry B1 to A3, B1 to A3, C1 to B3, and A1 to C3. These are output terminals, and this is the neutral. So can you identify the difference in connection between the previous diagram and this diagram? In that diagram also we have shorted the 2 terminals, and from 1 to 3 terminals are connected. But then what is the difference?
So A1 was connected with B3, but here the reverse is happening. A3 is connected with B1.
Yes, the order of connection has been changed, isn't it?
Yes, sir.
Okay, any question? So that's all about these phasor groups. So practice these phasor groups.
Sir, I had one doubt in DZ6.
DZ6. Yes.
Sir, in the phasor diagram, we have taken all the corner points B3, A3, and C3. That is due to 180-degree phase difference.
Yes.
Okay, sir.
You see, the direction of this arrowhead is from left to right, but this one is from right to left. That is why 180-degree phase shift. Anyone having any other doubt? No. Okay. So next topic is this operating principle of all these different types of connections. So star star, star delta, delta star, delta delta, these are very simple. We have to do this open delta connection more elaborately. Okay, so let us consider the first connection, that is star connection. So both no, let us consider this this connection first. So what is star connection? If we connect all the similar terminals, we will get some star connection. Okay, either all the 1 terminals are shorted, suppose A1, B1, C1, then we will get one star connection, or we can connect all the 2 terminals as we have seen from our previous discussion. So we can connect A2, B2, C2 also to get star connection. Okay, so here this shorting point, that is where we have connected all the 3 A1, all the 3 1 points or all the 3 2 terminals, that is the neutral point. Okay, so from this neutral point to any terminal, that is the phase voltage. So here VAN, VBN, VCN, these are 3 phase voltages. Okay, for star connection. And we can see between 2 terminals, suppose this terminal and this terminal, there appears 2 windings, this one and this one. Okay, so the voltage across this terminal and this terminal will be different from this phase voltages. So that is called line voltage. Okay. So what is this line voltage? Is it the algebraic sum of these two?
No, sir, phasor sum.
Yes, phasor sum, and we know that this is actually the root 3 times of this phase voltage. We have learned these things in basic electrical course. Okay, so the relation between phase voltage and line voltage is that VL equals to root 3 V phase. Okay, and the line current, here we can see this IB, that is the current entering through this B terminal, so it is denoted by IB. Similarly IC, IA, so these are called line currents, and we can see these line currents and phase currents, these are same. Okay, so in case of star connection, the phase voltage and line voltage are not equal. Line voltage equals to root 3 times phase voltage, but line current and phase currents are same. Okay. So from this phasor diagram we can determine the relation between line voltage and phase voltage. So three phase voltages are there: VAN, VBN, VCN. So VAB is actually the resultant of VN and the opposite of VBN, that is minus of VBN. Okay, this we can write from the connection diagram. Suppose this, let us consider this one, these two. Okay, so this is VAB. So if we write KVL equation, we can write VAB is equal to VAN minus VBN, because their directions are different. One is, suppose from neutral to the terminal is the positive direction, so this one are opposite in direction. So phasor sum of these two will give you the line voltage across AB terminals. Okay, so this we can write from here. Okay, so here the angle between VBN and VAN is 120, therefore this angle is 60 degree. So therefore the resultant we can write, so here all the phase voltages are taken equal because we are assuming balanced system, and line voltages are also equal, so VL will be the line voltage. So let us consider the calculation of VAB first. So VAB is equal to VAN minus VBN, which is we can use this formula, or even we can write this VBN equals to sum of the components of VAN along this line and sum of VBN along this line. Okay, so this component is magnitude of this VAN is V phase, which is, and component is V phase cos 60 degree, and this one is magnitude into cos 60 degree, that means 2 V phase cos 60 degree, which is root 3 by 2. So this 2 will get cancel out, will get directly root 3 times V phase, or we can apply this expression. Okay, so that is the relation between line voltage and phase voltage. So for a balanced system, all the line voltages are equal. So VL equals to root 3 V phase. That is the relation. And the currents are same for line as well as phase. So IL equals to I phase. So that is for star connection. Okay. So in a balanced star connected system, line currents are equal to phase currents, but line voltages are √3 times the phase voltages. This we know. Okay. Now delta connection. So this is our delta connection. From this diagram, it is obvious that phase voltages and line voltages are same. So let us consider this is one phase. So B1 to B2, suppose this is our phase voltage VB, which is also the voltage appears across this B terminal and C terminal. So this is VBC. So these two are same. So in case of delta connection, line voltage and phase voltage are same. But the line current are IB, IC and IA. But consider this point here, this IB is entering and getting divided into two components. One is VBC, that is this terminal. So this current is flowing from B to C, and here the current is IAB, which is entering. Okay, so IA is getting divided here. So one component is IAB, another is entering current here. Okay, so this current is negative for IA, this current is negative for IB. So don't think in that way. Actually, at this point, two currents are entering, IB and IAB, and leaving current is IBC. So if you apply KCL, you will you can write IB plus IAB is equal to IBC. So IB, that is the line current, equal to IBC minus IAB. All are phasors. So that means IB, that means any line current, is equal to phasor sum of these two currents. So you have to determine the resultant drawing the negative of IAB, as we have done in case of calculating the line voltage for star connection. Same calculation. Okay. So using this phasor diagram, we can calculate the line current IA. So let us consider all the phase currents are equal for balanced system. So here I phase is the phase current, and this is the KCL equation as I have already mentioned. And from this phasor diagram, the line current is equal to √3 I phase. Okay. So IL equals to √3 I phase, and VL equals to V phase for delta connection. So we can conclude that in a balanced delta connected system, line voltages are equal to phase voltages, but the line currents are √3 times the phase currents. So these are well known to you. So next we will be considering three-phase power. So this is also known to you that three-phase power is equal to √3 VLIL cos phi. That is the actually we can measure three-phase power by using two wattmeter method, but we can measure for a balanced system we can measure the single phase power, and by multiplying that by 3 we can also calculate the three phase power. Okay, so what is this three phase power? The total three phase power delivered to a three phase load is given as the three times the power delivered per phase. So each power is, suppose each phase is giving a power of P1, so the other two phases will give P2 plus P3. So if they are equal, so we can multiply them by 3 to get the total power. And if the load power factor is cos phi, then for a star connected system the equation will be P equals to 3 V phase I phase cos phi, and putting the relation of line parameters, we can write this as root 3 VLIL cos phi. Similarly, for delta connection, we have to replace this I phase by IL by root 3, so that we will get the same expression in delta connection also. So if the load is connected in delta, we will get the same expression. So therefore, it can be seen that irrespective of the type of connection, star or delta, the power delivered or consumed remains same for a given three-phase system. Okay. Power is generally expressed in terms of line voltage and line current, since it is convenient to connect voltmeter and ammeter in the line that are external to the device, rather than in phase coils, which are often inaccessible. Okay, we can express the power by this equation also, but it is very difficult to measure V phase and I phase, because we cannot connect some voltmeter inside the system, or we cannot connect an ammeter to measure the per phase power. Okay, so here it is easier to access the output terminals, which is external to the device, and we can connect some voltmeter across the line terminals, and we can connect ammeter in series with the line terminal. Okay, I mean in series with line. Okay, so that is why we use this expression, because VL and IL are easily measurable. Okay. Okay, today up to this.